All right, so today we're going to talk about measures of dispersion, which is section 3.2 in the book. And if you remember last time, what we talked about was the measures of center. Measures of center are supposed to give you this idea about the measurements that you took on some observational study. We measured cinnamon sticks last time. And what you might notice is that even though the mean and the median and the mode describe the data, sometimes what it's missing is how spread out the data is. Remember, our mean and our median and mode were all pretty close to each other, but it didn't really describe the way that the data went all the way down from 2 inches up to 11 inches for the soft cinnamon. So here we can see the cinnamon lengths from last time. So we went to Honeybee Market and we saw a bunch of different cinnamon lengths, anywhere from 2 inches to 11 inches. And then at Trader Joe's, we saw a bunch of different cinnamon lengths. Well, actually, we only saw two. We saw 2.5 inches and 2.75 inches. So what I mean by dispersion is that even though the mean, the median, and the mode were kind of towards the middle numbers, what we have is that on the honeybee side, we have that we go as low as 2 and up to 11. And that was not able to be seen when we just talk about the mean, the median, and the mode. For Trader Joe's cinnamon, it goes from 2.5 to 2.75. So there are different ways to describe that dispersion, how the numbers spread out. So the first measure of dispersion is called the range. And what the range allows us to do is it allows us to see how much spread there is between the values. So the range is where we take the maximum value and subtract the minimum value. In the honeybee cinnamon, what we saw was that the maximum value is 11 inches, the minimum value is 2 inches, and so if I subtract those numbers, I get 9 inches. So the range for that one is 9 inches. What that says is that there is 9 inches between the smallest piece of cinnamon and the largest piece of cinnamon. For the Trader Joe's, we had 2.75 was the maximum value, and 2.5 was the minimum value, and so I get 0.25 as the range for that. This immediately shows me that there is a big difference between these two different sets of cinnamon. The larger, the soft cinnamon from honeybee has a gigantic range compared to the Trader Joe's cinnamon. And so we know already that the different sizes of cinnamon that you can get from honeybee, they can be all over the place. Whereas for Trader Joe's, because they're within a quarter inch of each other, you really don't have that much difference between the pieces of cinnamon. You can almost imagine that that's going to be, and we saw cinnamon of the same length. The second way to kind of look at the dispersion is using what's called the standard deviation. And the standard deviation for a sample is a lowercase s. If you were to do it for a population, so let me just kind of put this down. If you're looking at the population standard deviation, the parameter that we're trying to get, it would be, it looks like a fancy S. It's the Greek symbol sigma. So when we're looking at the standard deviation for a sample, what we're really doing is we're kind of taking a sort of average of the distance between each observation and the mean. So the xi's, so this part right here, this is just each individual observation. So that's each individual measurement on the cinnamon. The x bar, remember that's the sample mean. So what are we going to do? We're going to subtract, we're going to take the observations, subtract the mean. That tells us how far the observation is from the mean. Then we're going to square it. And what that kind of does is it allows us to make any negative values positive. Because when you square a negative, you get a positive. When you square a positive, you get a positive. Then we're going to kind of take an average. So when you take an average, you add them all up. That's what this capital sigma is. You're going to have a bunch of numbers. You add them all up, take their sum. You're doing an average, so you're going to divide by n minus 1. N is the number of observations. The subtract 1 is kind of, the way I see it, it's kind of fixing the idea that we've actually done this squaring thing. And the other thing that's going to fix it is when we get to the end, we're going to take the square root. So the way that I do this is I typically use a table. So on the next slide, we'll see a table, and we'll go through with our honeybee calculation. So here I have a table, and in this table, we see that we've got a column for the xi's, that's the observations. So remember these honeybee, we had 2 inches, 2 inches, 2 inches, 2 inches, 2 inches. We had 5 2-inch pieces. We had 2 3-inch pieces. We had a 4-inch piece. We had a 6-inch piece. We had 2 7-inch pieces. We had a 9-inch piece, a 10-inch piece, a 10-inch piece, and an 11-inch piece. So I'm going to fill in that column with just the raw observations from what we saw the other day. Now, when I look at these observations, what I'll notice is that what I need to do, had I not computed the mean, was I need to add them up. So on this last row, I call this the sum row. So I add them all up. So remember when I add these all up before, I got 80. And the reason I might do that is because now, if I want to find the mean really quickly, I just take x bar is equal to 80 divided by the number of numbers, which in this case was 15. And that gave me that 5 point, what do we have for the mean last time? I think it was 5.3. It was 5.3 repeating. I'm going to round it to the nearest tenth for this. You will have different roundings depending on how close you need to get. But just for the sake of speed and for this, we want to focus more on the calculation. I'm going to round to the nearest tenth. So for this next row, what we're going to do is we're going to take the observation. So in the first one, it's 2. Let me make that darker. So it's 2. I'm going to subtract the mean, which is 5.3. And that's going to give me the number, negative 3.3. So that's what I'm looking for in that first row, first column. Negative 3.3 is what I get when I take the observation minus the mean. For the next one, 2 minus 5.3 is also negative 3.3. And then negative 3.3 again, negative 3.3 again, negative 3.3 again. And then when I take the 3 minus the 5.3, I get negative 2.3. And then 3 minus 5.3 is negative 2.3 again. 4 minus 5.3 is negative 1.3. 6 minus 5.3 is 0.7, 0.7. And then 7 minus 5.3 is 1.7. 9 minus 5.3 is 3.7. 10 minus 5.3 is 4.7. And 11 minus 5.3 is 5.7. Now, I typically also add these up. And when I add them up, I get 0.5. The reason I do it on this row is that what I should get is I should get 0. When I add these all up, I should get 0. Now, the reason I'm going to be okay with the 5.5 right here is that it's close to 0. It's close enough to 0, and the reason I know it's close enough to 0 and not 0 is because of the rounding. Had I gone through and rounded to the nearest hundredth or thousandth or so on and so forth with the mean and then these subtractions, I would have gotten closer and closer to 0. And the reason I want it to be close to 0 is because it gives me the idea that I probably did the calculations right. So that looks like these are supposed to be pretty good numbers. So the next part, I'm going to square. So for this next column, negative 3.3, I'm going to square that. And what I get is I get 10.9. And again, I'm rounding to the nearest tenth. And the further down you round, the better for the calculations. For this, with how much room we have, I think it's good to focus more on the process than the rounding. Though if I was doing this for myself, I would definitely be rounding much, much further down. Negative 2.3 squared is 5.3. Negative 1.3 squared is 1.7. 0.7 squared is 0.5. 1.7 squared is 2.9. 3.7 squared is 13.7. 4.7 squared is 22.1. 5.7 squared is 32.5. And we don't square the sum. What we're going to do is we're going to add these all up. So when I add them all up, I get 163.5. Now what I've done so far is I've taken each of the xi's and I've subtracted the mean, and I've squared them, and I've added them all up. So what I have left to do for that standard deviation is I still have to divide by n minus 1, and then take the square root. So then what I'm going to do is I'm going to take that the standard deviation for this one is equal to the square root of that sum that I just got, 163.5. So that's what I get when I took the sum of all the squared deviations. So that middle column, I call those the deviations, or how far off they are from the mean. And that last column I call the squared deviations. I have to divide by 15 minus 1, because 15 is the number of observations, and then I have to take the square root. And when I do that, when I take 163.5 and divide by 14, I get 11.7, and then all together I get the standard deviation is approximately 3.4. So that standard deviation tells me that the values are about 3.4 away from the mean. It gives me a good feeling for what's going on here. Those values are able to spread out. For the next one, I'm going to start this one out, and you could try to finish it. So this is for the Trader Joe's one, and it's really not half bad. So I had that the observations were 2.5, 2.75, 2.75, 2.75, 2.75, 2.75. When I add those up, I got 16.25. And so my mean is equal to 16.25 divided by the 6, which is equal to 2.71. 2.5 minus 2.71 is negative 0.21. 2.7 minus 5 minus 2.71 is 0.04. 0.04, 0.04, 0.04, 0.04. Now when I add these up, I got 1, 2, 3, 4, 5 0.04s, and then so when I add them up, I get negative 0.01. That's pretty close to 0, so it looks like my calculations are okay, and it's really close to 0. Now I've got to square each of them. So when I take the 0.21 squared, I'm going to put that in this spot right here, and then the 0.04 squared, and keep on putting those in those spots. So remember when we get to the end, and I'm going to leave this part for you to try out. When I get to the end, I'm going to add those all up to get the sum, divide by 5, because n in this case is 6, and then take the square root, and that gives me a standard deviation. What you should notice right off the bat is our standard deviation cannot possibly be very large. And the reason why is because when I square something that's smaller than 0, I get something that's really even closer to 0. And if I add those all up, I'm going to get something pretty darn small. And if I divide by 5, I'm going to get something even smaller. And if I take a square root, I'm going to get something really small. It's going to be something like 0 point something. And that's not surprising because most of these cinnamon sticks are the same size, and that's what the standard deviation tells us. The last part of this lecture is what's called the empirical rule. The empirical rule tells us one of the reasons why the standard deviation is so powerful. The standard deviation is a good way to describe, we can use the standard deviation to describe data that fits a bell curve, which is a symmetric curve that looks like a bell. You can see that this curve looks like a bell. It turns out that in the population, 68% of all observed values are within one standard deviation of the mean. 95% of all observed values are within 2 standard deviations of the mean. And 99.7% of all observed values are within 3 standard deviations of the mean. So here I want to show you an example of what that means. If the mean weight of a tiger is 400 pounds and the standard deviation is 30 pounds, then one standard deviation above, so if I want to talk about just one standard deviation, one standard deviation above would be 430 pounds, right? If I add the standard deviation to 400, the average, I've gone one standard deviation above the average or above the mean. And one standard deviation below is 370 pounds. So anything between 370 and 430 is within one standard deviation of the mean. 68% of all tigers are between 370 and 430 pounds. That's what this is saying. The weight of a tiger, it does fit a bell curve. And so this distribution, a symmetric bell curve, tells me that 68% of all tigers are between 370 pounds and 430 pounds. If I went 2 standard deviations away, down to 340 and up to 460, so anywhere between 340 and 460 pounds, 95% of all tigers are within there. And 99.7% of all tigers are between 310 pounds and 490 pounds. Now, why that's important is because if you were to find a tiger, an adult tiger, who is 550 pounds, they are in that very, very small tail on both sides of this graph. And what that means is the likelihood that you just have an average tiger or a tiger in that range is really unlikely. So we would say that this tiger must have something that we might want to look at what's going on with their diet, why they're so much heavier than all other tigers. Or, similarly, if we had a tiger that was only 300 pounds, this is going to be again inside that tail, and we might wonder if there's a nutritional problem with this tiger as well. It allows us to kind of compare to the rest of the data, realizing that it's so far outside the data set that we would expect, it sends up a red flag and we can kind of look at it. So the standard deviation is an incredibly powerful tool. I'll see you next week.